All right, here we are at it again. Trying to understand the control Z. So we're gonna do the following just as a basics. We're gonna go and just stay with 2 qubits. And I had trouble last time visualizing the control Z by using that here. So I'm gonna go ahead and assume that if we do this and this and this is the same as doing a control Z. This is based on the notion that doing a I think that's something that's safe to assume. And I'm gonna just keep that in here. Let's see if I can edit that and include that as well. So we know that this is the control Z. It's just for me to be calm with this. And then we'll edit that and include this as well. Okay, and no, we're gonna do it like this way. So there's a control Z. And what I want to do now is I want to do 3 things. So I want to try to understand by using the visualization tools that the IBM Q experience is providing us here is what happens first against all the possible classical states. So let's assume 0, 0 is 1. 1 possible state, 0, 1 is another one, 1, 0, and 1, 1 is the other one. So 4 different possibilities. Then we're applying a control Z, and then let's see what happens. Then I want to see what happens when we have sort of a non-classical superposition, but it's still without any type of entanglement. So when this means when each qubit is in a superposition. And then we're going to entangle them and see if that brings any more clarity. So I have no idea how is that going to work out, but let's see. So we can see already that so what I'm seeing here is when they're in 0, 0 and we're having a control Z, then nothing happens, which makes sense because the qubit 0 is 0, therefore the control is not activated, therefore the Z is not applied. Now, if I'm doing something like that, problem with my mouse. So I'm going to do something like that. Now we have a 0, 1, right? I think I want to make sure that maps the. So what are those zeros? The qubit 0 is the one that is farthest to the right on the state, farthest to the right. Okay, so that qubit 0 here is the 0 here, like the last the sort of the rightmost. Good. So here we see nothing changed. If I have to be careful because I know that in some representations, if I got to tackle a state vector, so nothing changed because. So what that tells me is that the Z doesn't do anything to a qubit that's in a classical 0 state because that's a 1. So I'm assuming then this is applied. Now, if we do it this way, we're also going to see that nothing happens because of the same reason that we said before. So my understanding here is 0 means this control Z is not activated, so nothing happens. And we do this. Now what? Also nothing happens. Nothing happens with the state. Nothing happens. Which basically, it kind of makes sense because the Z gate so if I imagine a block sphere and I'm saying the Z, I mean it doesn't matter, but it's just rotating the Z axis of the block sphere for 1 qubit. I keep going back to the block sphere, and I think that's dangerous to do, especially with 2 qubits. So I'm going to try not to do that. But basically, what we just saw is that to any classical combination of states, it just nothing happens, right? Which is already a good outcome to keep in mind. So nothing happens. Now, what happens if one of them um, is in a superposition. Now I'm gonna leave the qubit 0 as a like, with an X gate, so we make sure that the control Z is applied, because otherwise it doesn't make sense, right? So we can already skip those cases where here we have a 0, because then nothing's gonna happen. So what if this is in a superposition? What have we got? Basically nothing. Really? That's so confusing. Nothing? Yeah, well, basically what, because what this is telling us is, at the end of the day, what can happen if the Z doesn't have any influence on either 0 or 1, but it does in a superposition. So confusing. That is confusing. Probabilities is all the time 0, 0, 0, 0. So what if this is here? It was 0, nothing happens, and then we add an X here. Also no. Again, I hope this is again something is wrong with this or what. Unless I'm again, there's something I don't see, which is basically maybe, to see anything. So this is telling me is that this is maybe not affecting anyhow the qubits in the base, in the computational base Z. Is that so? Or am I again experiencing some sort of buggy behavior? Nothing. Absolutely nothing. Marvelous. Now, what if we entangle them? Boom. Maybe those barriers are like... That's getting paranoid, man. That's getting paranoid. Let me see. It seems maybe there's some just issues with this visualization. It just doesn't seem like it's awkward. So if I save those changes and I run this on a simulator, see what we get. See what we get. Pending results. It's kind of weird. Kind of weird. What if I just remove that? No, it doesn't bring anything. It doesn't make a difference. It doesn't make a difference. And so we got it ready, and then I open those results, and what do we see? Interesting. So let me just go back to square one. So we've got that. Good. What happens if we measure on the Harman base? So wait a second. Density matrix. And now I'm going to do this, and I'm going to do this. Something's not working right. Something's not working right. It's impossible. Something's not working right. Simulator. And we're gonna do this, and so I'm just trying to speed things up a bit. So I'm gonna do this and that, and now see what happens. Oh, I'm an idiot. Well, obviously Obviously, I'm not going to measure anything if I don't measure anything. That is obvious. So let's check what's going on here. So what if I do this and I send this to run, and it's in the simulator run. Okay, so now we're measuring. So that's still a pending one. So I'm going to ignore those two results here. It's a pity that this is not working. I should try with another browser. Okay, so let's take a look at the results. So now we've measured on the Hadamard basis, and we see that. That tells me nothing really. Let me get rid of those guys, because that's a Control Z, right? So let's simulate that again, see what we get now. And to speed things up, I'm going to try with this, and I'm going to run that also. Good. So here we've got the first results. Oh, state 1, 1. Okay. Well, yeah, it basically has done nothing. It basically has done nothing. And now we've got those which might be a bit more interesting, which is we've got an entangled set of entangled qubits, and now we are applying that. Let's see what's going on here. And it looks like it does nothing. How can that be? I'm extremely confused. I'm extremely confused. So I'm really extremely confused. So what if we'd say, let's just clear. Let's start from scratch. Good God. It's probably at my end, but so let's start from scratch. So we've got this. I mean, does this thing change at all? Yeah, okay, so now it seems to work in ways that maybe when I'm doing stuff like replacing things here, it just has problems recomputing that visualization. But basically, what I was the most interested in was what happens when we have like a superposition. So this means, all possible values are possible. And now we're going to do Control Z, which it translates to that. Okay. Now we're talking. Why didn't that work before? Why didn't that work before? I'm a bit afraid that it has to do with, updating these and then this being updated somehow. So what's happening here is basically that what's happening here. So we keep, it seems like we keep the same. So we keep, a superposition, but what we're doing is we're flipping the sign on the 1, 1 case. So we're flipping flipping the sign. I mean, phase. I don't know. We're doing something. So that is then okay. That's an interesting case, because now because now I'm going to go ahead and do something, but I don't know if I have to start from scratch again, or because if I remove this, what happens? So 0, 0, 0, 1. So what happened now, basically, that is what happens when you're doing a control Z on a 0, where and then the first and the control B is a Hadamard, right? So really nothing. If I add a next here, yeah, that makes sense. So whenever it's 0, it stays the way it is, and it flips the sign. So it seems like it's flipping the sign. It's interesting, even if there's nothing else, it seems like flipping the sign. The 1, 1 density matrix. So that definitely means those are the two possibilities. Which without that, it's kind of funny, because without that, it's then this here. But with the next, it's then these two guys down here. So if you think about, because I know the meaning of a Z gate, I know the meaning of a NOT gate. The problem is when you're at the control thing, you're making the qubits talk to each other in the sense that you're creating correlations. So I'm trying to understand that's for me the extra meaning of the control Z, right? What type of correlations we're creating. So it seems in this case you're creating a type of correlation where they agree or disagree with the same probability, but there's something else to it, because it's not always the same type of agreement. Look at this. You could say, so what I could say is that the qubit, the last qubit always agrees. What have I just said? I don't know. So this is always 1, and then this is 0, 1. This is always 1. Yeah, of course, because it's a Hadamard here. But it's difficult. I don't even know where to start reasoning. Because obviously the entanglement happens not just when you talk, so not just because of the control Z, but because the control bit is in a superposition, which then basically that creates the correlation, right? That's not, it doesn't happen otherwise, because if I just, as I said, we just do that, that's nothing, right? So that basically it doesn't affect anyhow. This also doesn't affect this anyhow. Removing that just doesn't affect anyhow, and then the control Z doesn't have any effect on states that are not. So you're not creating an entanglement. And then in the cases where you are creating a superposition, so this means that both qubits are not entangled, but they are in a superposition. In that case, there is something happening, which is that the sign of the possible outcome 1, 1 changes, right? And I can see that because also here is red, right? So if you think about, blue would be because this is not whether they agree or disagree. It's just the phase is negative. because that's what we can see here, right? So that this is like that. So curious. That's a curious one. And now, if we just say we entangle this way, right? And maybe it makes it easy to visualize if I do something like that, and I do like that. And so what I'm meaning here is, so we do this in the control knot. So if we're doing that type of correlation, this is what happens, right? So remember, in the when you do an entanglement with a control knot, what you have is they always agree, both qubits. And here is that they don't always agree. And if I add an X here, then it's, I think that's again one of those issues, correct? Because that should definitely switch these two columns. It's difficult to play with that if it's not working well. If I send that for a simulation, let's see what happens. But that's my understanding, is that then you would have that type of correlation. So basically, I don't know how you describe that correlation, but they agree and disagree with the same amount of probability, but not all the outcomes are possible. It's like it's definitely okay. Let's see what happens. Yeah, so 1 0 1 1, as I said, those are the two possible states. Good. At least my intuition here was right. So I think there's something wrong with that. Is there a way to refresh this? Maybe it's just a matter of switching these, and it seems like it's just a simple. It should be like a simple thing, where this is saved. So what if I reload? And still doesn't work. I'm gonna have to be running that, so let's see. Okay, so but anyway, so basically then maybe that will make it easier to understand the whole thing as well. Not here, we want it here, no, this, exactly. So this is the control set, this is we're preparing the first state, and then this is the measurements. Good. So if so the live visualization is definitely a really good help if it works. Otherwise I have to run the whole thing every time. But interesting. So it's a different type of correlation. What's happening? And if it's funny because those are like start playing with this. Okay, so this is, you're creating a Hadamard here, and because if I do something like that, what happens? So basically now what I'm saying is do that. You say yes, but you have a Hadamard. Just curious, what happens? I want a simulator. So this is one thing. What happens with, so if we create more complex states, just like something weird, like instead of a Hadamard, we're gonna create a rotation, or we're just gonna add some rotations across all the different axes, however that really works, X, Y, and Z, of, I don't know, something like that, and something like that. So it's kind of like a completely weird, I would say it's not a really clean state in terms of like, it's an equal superposition. So I'm going to run that as well against the simulator, see what happens. Just I'm playing with this, okay? I really, because I'm trying to find even a way I can just try to, in a more organized way, figure out what's going on. So basically this has been finished. So this is what we were doing here, and what's going on. 0, 1. Oh wow. So this is between 0, 1 and 1, 1. So intuitively, what this seems to be doing is it's basically creating a correlation between the two qubits where half of the time they agree, half of the time they disagree, but whenever they always agree, it's always 1, for example, right? Or you could say the qubit 0 is always 1 in this case. Yeah. So when the qubit 0 is 1, then you're going to create a correlation that is basically, well, this is always 1. So I really, aside from the fact that it's creating a different type of correlations than like a Bell state where they always agree, or there's also the correlation where they always disagree, I have a hard time understanding intuitively what's the benefit, aside from just creating correlations. And obviously we've seen that it flags, if we have a superposition from both qubits, it basically flags the 1, 1 state. So that's a helpful functional. I see some more like a helpful intuition there, because then you could do things where like you're flagging things for a certain purpose within an algorithm or solving a problem. And here, so we've done a weird rotation. Cool. So basically it created a final sort of a result where most of the time it agrees that it's 0, 0, and sometimes maybe from the standard measurement perspective, it seems to me that it's safe to say that the control Z gate basically creates a type of entanglement where the two qubits, they agree or disagree half the time. But that doesn't, again, include all types of agreements and disagreements. It doesn't convince me, but it seems to be this way. Now, I guess where the IBM guys are going when they are like, what happens when you measure that from a Harama perspective. No, here. So you do like a measurement on that base. Say from like let's say we go for these where we know that what the control Z is doing here is flagging the 1, 1 state, right? So if we run that, because now we are going to measure it from a different perspective. So we run that against the simulator. And I'm going to do another thing, which is I'm also going to take this measurement, which they point, so the guide points to this measurement as being, okay, now with this measurement, we have the complete picture of how to represent a 2-qubit system. So the normal measurement, the Z measurement, the Hadamard measurement, and then the one with the S transpose. And I don't like, I feel a bit tempted to go down to the mathematical level, put some matrices here and there, and then see what happens really under the hood. But I want to try to understand that from an intuitive perspective, because I think that's definitely the, that's what that's what's challenging, by the way. Okay, so let's see. So we've got, I think, already both results. First, this one, that's from the Hadamard perspective. Oh no, that's still, oh sorry, I haven't submitted this one. What am I doing? I haven't submitted this one, so I'm going to submit this for run to the simulator. And while this is running, I'm going to check this one. So this is, in a superposition, and we measure from the Hadamard gate, and okay, yeah. So it's funny, because basically what this is saying is that from one perspective we are kind of flagging one. So we're switching a sign in the state 1 1, but if we take a look at it from a Hadamard from another measurement basis, then we are basically getting again a uniform superposition. We're just getting a uniform superposition. Interesting. The thing is, yeah, intuitively, this concept of measuring from different perspectives is, I'm still having trouble with that, because I don't see the utility of this. Maybe aside from understanding, I don't see the functional utility of this. Why I keep going back? I have a lot of stuff open, but let's take a look at the last one. So this is what happens with this basis, right? Boom. They always agree. So so they always agree. So this means that that's obvious. The way you take a look at things changes the way you're going to see the results. But basically, it means that a control Z seen from that perspective it's an entangled state where they always agree. It's like the belt state. But to be honest, I don't know what to do with that. I don't know what to do with that. To me, it seems like the so far what I got out of this is that the control Z gate gives you a different type of entanglement. Because I bet you that if I would generate a belt state and I would take a look at it with this measurement, and we're going to get the same that we are getting, you know what I mean? So if I go and I say, let's clear that thing, and I say, now we're going to do this and this, and now we're going to create a belt state. So we're going to say that is just a uniform superposition where that is an entanglement where they always agree. Now I apply a control Z. I'm ignoring that for the moment because I don't know if this is really correct or not. And now I'm doing the measurement of that helps me. I think that doesn't make anything, but it just helps me visualize where the measurement is. So now I'm going to do this. I'm going to do a Hadamard, and I'm going to do a Z measurement, and I'm going to do this, and I'm going to take a Hadamard, and I'm going to take another Z measurement. What? Here. And I'm gonna run it against the simulation. I don't know if I know what I'm doing, honestly. That gives me the same. I don't know what I'm doing.